Thank you, everyone. It's a pleasure for me to be here and to be hosted here in Munich. So today, I want to give an update on what I think is state of the art in autonomous driving. What are the main questions or debate that are still being discussed in the industry? And so quick introduction about AID, Autonomous Intelligent Driving. So we are a subsidiary of Audi here in Munich, founded last year. The approach is to say that this needs to be a separate group from the main Audi Volkswagen development centers and to leapfrog the technology. So no incremental approach where you go low speed, you progressively increase the speed, and you start with highway and then you extend and so on, but have a group that right away looks for level 4 autonomous driving system. And so we are developing the technology for the whole Volkswagen group. I'll show a couple of examples of projects that we're working on. And I think with the fundamental goal of trying to marry the automotive industry and the high-tech and software industry, which I think is actually pretty challenging if you're familiar with these two industries. But I think it's the only way that you can really solve this problem. You need to get the both of these two worlds, and any one of these worlds separately will not be successful, in my opinion. So that's a quick introduction. So then I want to share a little bit of the vision of why autonomous driving has like the potential, and actually you'll. If some of you have been to the Lilium speech just before, like I was, you'll see some overlap there, so that's very interesting. And then give some example of what it could look like concretely, and then I'll deep dive more into the technical side. What are the big key technical questions still open today? Yeah. So that's what a city, typically more like North American city, would look like today. With essentially a lot of space dedicated for parking lot, because everyone is just commuting by car and you need to put this car somewhere, and it's just taking a lot of space, pretty much low value or no value space within an urban environment. And that's what it could look like tomorrow. You could have more building, but you could also have more green space. If you have more building, you're increasing the density. If you're increasing the density, you can reach more people with less transportation, so it lowers the need for transportation, and so you need less cars, less transportation. And then, of course, you can use also this space to breathe more, to have open space, green space. On a European city, it would look more like this. Where lots of parked cars, as you probably heard before, like cars spends 90% of their time or 95% of the time parked unused. That's kind of a waste. And then of course, if you imagine that this is now replaced by shared cars, shared autonomous cars, it could look something like this, where you just have a couple of pods moving around, and these cars are actually driving 90% of the time. And then you can use the space for more space for pedestrians, for bicycles, or other lean way of transportation, and of course more green area, more just air to breathe. So brief reminder for people who are not familiar with the different level of automation. This is coming from the SAE, Society of American Engineering, how they classify the different level of automation. So level 0 is no automation. Level 1 is basic driver assistance, so like ACC, adaptive cruise control. This is now very common on most cars, right? Even it's not just premium cars, but many cars have this today. Level 2 is partial automation. So this is typically autopilot from Tesla, but also Super Cruise from General Motors, and most constructors have, most OEM have something today. So you can be hands-off for a few seconds. You're not supposed to be hands-off, but the thing will work hands-off. But you definitely have to monitor the system. The system will make a mistake every maybe 100 kilometers or something, and so you have to be ready to catch up. So this moves the driver from a operator role to a supervisor or monitoring role. So you don't have to do the closed loop, watching the lane marking, watching the speedometer to always, be centered in the lane, always be at the speed that you want to drive. So you don't have to do the slow level control, but you still have to do the monitoring of the situation. You have to see, okay, cars merging in front of me, someone is stopping harder than it should, something's coming that is not handled by the system, and be ready to take over. Level 3 is basically when the system can handle most situations, so the driver doesn't need to monitor and be ready to take over at any time. But the system can fail, but it can detect the failure and then ask the driver to come back. So typically we talk about 10 to 30 seconds for the driver to come back. Typically you notice that you lose a camera or you lose a sensor. You have enough that you can continue to stay in the lane, but not for very long. And so you beep the driver, and the driver has to drop his laptop or his cell phone or whatever he's doing. And come back, but I see some people smiling. But so in level 3, it's actually okay to use your laptop and your cell phone. Here, it's not okay, and so if some people are doing it, you should definitely stop doing it, because that's why we have issues today where people think they have a level 3, but they really have a level 2, and that's one of the big issues with level 2. Level 4 is basically you don't need the driver for failure. The system has enough redundancy that even in case of a failure, it can still continue to operate. And the limitation in level 4 is that you cannot drive everywhere. So it's defined condition. Typically, it will be on highway, or it will be in a geo-fenced area in an urban environment. Maybe also like the speed is limited, or the weather, you don't handle snow, for example, but it's something known in advance, and the system can detect, okay, now I'm going to reach the end of my, we call it ODD, operational design domain, and is going to go into a safe state, and then the driver can or cannot take over. But in normal operation, in level 4, you can go to sleep. Like you don't have to be ready to take over, because the system will always be able to end up in a safe state. And then level 5 is the full automation. So the system can go anywhere, anytime, any condition. This is technically really far away, because it technically means the thing can drive in New Delhi, India, for example, as well as in Germany and the US. And so that's pretty far. But I think with level 4, that's really within reach, and that already enables a lot of use cases. This is an example. So the new Audi A8 that was released last year is the first level 3 capable car. So here's a description of the different sensors that it uses. So now it has a laser scanner, Lidar, in the front. That's the first one, the first Lidar in series cars. And then more classical sensors, ultrasonic sensor, radar sensor, camera. What's new with camera is that now you have 360-degree cameras. And radar also, the innovation is that also you have 360 on the radar. So you have traditional long-range radar in the front, but now there's corner radars as well to detect cars coming from the back and from the side. So this is shipping today. The more futuristic design, but that are real. I mean, like the prototypes have been shown at the Geneva Auto Show last year, and there's we're actively working on this project. This is how an urban taxi, robotaxi would look like. So you have a nice interior. Now there's not any steering wheel or like driver's seat anymore. It's just 2x2 facing seats, and this would take you from A to B within the city. So kind of my taxi or Uber, but without a driver. That's another concept from Audi, the Icon. That's the kind of the equivalent, but for long distance lounge. Let's say you want to go to Stuttgart. You book this car. It comes to pick you up, and then the interior looks like this, with also no steering wheel and pedals, and you can sleep or work or have a conference or something on your way to So now going a bit more into the technical detail, because this is a big tech day. So this is the high level different pieces that you need to build an autonomous car. We'll later do a deeper dive on the embedded part, or the part that's on the car. But it's very important to keep in mind that now it's a whole system, and the part in the car is just one part of the system. You have a lot of things happening in the back end, whether it's in the cloud or on premise, but in the back end, and both for development, for continuous improvement, and also at runtime. So these are things like the data collection, so that we can improve our system, we can validate our system. We need to store all of this. This is a lot of data. We've been doing some calculation, and it's going to be in the hundreds of petabytes. So you have gigabyte, terabyte, petabyte, and potentially up to a hexabyte, which would be a full data center. Yeah, it's just a lot of data. And then we're going to talk later, but we need to train our deep neural network. We need simulation is going to be a huge part, of course, in the development and the validation of self-driving cars. And yeah, I mentioned the validation. And then at runtime, we need to update all these pieces because we're going to continuously learn, and we're going to continuously improve the system. So the map needs to be updated. I'll talk more about the maps later as well. But typically there is now a new construction zone. We need to update the map to say, okay, that now the lane deviate, or that this road is closed, or whatever else could happen. Of course, software updates, and also neural network updates. For the detail on the car, I have a zoom-in slide. So if people are doing robotics, this is typical robotic architecture. So you have sensors on one side, then you have intelligence, and then you have actuator on the other side. The actuators on the car, it's basically the steering wheel and the braking and acceleration, so for longitudinal control and lateral control. On the sensor, I think I mentioned already most of them. GPS is obviously one as well. And there could be other sensors coming, but these are definitely the most important ones. Then perceptions. There's different things that we need to do to perceive the environment. We need, I think the most important is to detect first the objects, like are there obstacles, are there things around us? If they're moving, we need to track them. So from frame to frame, is this the same thing that I've seen before? What's the velocity, what's the direction, and so on. Out of this also, we get the free space with all the static obstacles. I mean, it's basically where there's no static obstacles. And then you need other things like lane detection, you know where the lanes are. They're coming from the map as well, but you wanna fuse them to make sure you have information, not just theoretical information, but actually measured information. And of course, traffic signs, and more importantly, traffic light. Traffic signs also can be put on the map. They don't change that often, but it's still good to know that they're to see them in case the map is out of date. And of course, traffic light, this doesn't work on the map, so you need to detect them. And for traffic light also, it's very likely that you need connection to the traffic light, because out of all these sensors, only the camera can see the state of a traffic light, so it doesn't have any redundancy. Plus, it's actually a pretty hard problem if you start paying attention. It's not common that there is just a truck parked in front of the traffic light, or some other obstruction that you cannot just see the traffic light. You have some weird case also in places with lots of traffic lights where you could be in an alignment where the next traffic light is almost aligned with the traffic light in front of you. So that makes it very difficult to detect. So we'll need redundancy for traffic lights as well through connectivity. But this is actually happening on its own, because most cities now have their traffic light connected. And so we just need to have access to this traffic light control center. So that's your perception, capturing everything that's around you. Then like another interesting topic is prediction, like for all dynamic obstacles, dynamic objects, like typically cars, any vehicles, cyclists, but more importantly pedestrians. You need to get a sense of what's the intent. Are they going to cross the road, or are they not going to cross the road? So I'm going to talk a little bit more about prediction, because this is a very important part and also a very difficult part. And then since you're using a map, you need a localization part as well. Essentially, you need to know where you are on the map. The GPS for this is not enough. It will give you a precision of typically a meter or a couple of meters, but you need to be within a couple of tens of centimeters. So we use techniques like SLAM and basically put some features on the map that we can use to with our perception system to triangulate more precisely where we are on the map. And then we save all of this in an environment model. So we create a model of the environment around us. And then once we have that, we can do a trajectory planning within this environment. So I guess environment, both like current environment and from the prediction, like the future environment. And then the trajectory planner, it's going to find a way through this maze and generate control commands like a trajectory. And then you have a small controller that close the loop between the steering wheel and the longitudinal control on the trajectory that you want to follow. So that's the high-level view. Now I'm going into like some of the industry questions. So one of them is LiDAR or no LiDAR. Actually, it's not so much of a question. I just read a survey yesterday that I think like 90% of experts in the industry believe that LiDAR is needed. I think Tesla is one of the big exceptions. And but I'll give you a little bit more detail. So on LiDAR, there's different kind of technology on LiDAR. And actually, even before I go that, it's interesting also to mention, I said on the A8, it's the first production version of the LiDAR. So there's been, actually, it's not quite true. Like in the industrial world, there's been LiDAR around for many years now, but they're not suited for automotive. They're mostly 2D LiDAR, so one line. And like the design for industrial, so like super heavy, super bulky, would be difficult to integrate into cars, and the cost is also not where it needs to be for automotive. There's been Velodyne around for a long time. They have very good product for research, but up to today, nothing that can be integrated in the car. And so there's actually been a lot going on in the LiDAR space, I guess in the last couple of years, but it's really become visible. I would say over the last year, a lot of startups went out of stealth mode, and now there's like dozens, or at least a dozen, more than a dozen LiDAR companies out there, plus all the tier ones have their LiDAR projects. So there's a lot coming on, but today, if you want to integrate something in a car, there's nothing, I mean, except from the one that we saw before, there's nothing else that you can integrate into a car. But a lot is coming. There is different technology. One of the main differentiator is the scanning mode. So a LiDAR, typically you have one laser, and then you need to scan the wall to get a 3D view. And there's different ways to do this. Either mechanical scanning, so with like a mirror that just moves, or you put multiple LiDAR, multiple laser, and you make them turn. That's been the Velodyne approach. Now some companies are using MEMS, microelectromechanical systems, so very small mirrors to do the scanning. And some other companies are actually trying to go away from the scanning by doing what's called flash LiDAR. So think of, it's actually more like a CCD, like a regular camera, but you just illuminate the whole scene with infrared light, and then you measure the time it takes to come back for each of the pixels. Here's some pros and cons of the different technologies. So with scanning, you can get high resolution. The flash LiDAR are typically still in the 128 by 64 kind of resolution. The scanning systems are more mature. The one of the issues with the flash is the shorter range, because you need to illuminate the whole scene at one time, and you still need to be eye safe. The amount of energy that you can put is limited, and so the amount of light that you can go per pixel is more limited than if you do a scanning mechanism. But the benefit is that there is no motion compensation, because if you're moving while you're scanning, your image will be distorted, because all points are essentially taken at a different time. And also you can have a much faster frame rate, because you can take an image every millisecond if you want. So flash LiDAR are typically very good for around the car, short range. They have the potential also to be more reliable, because no mechanical part. And in the long run, they can be cheaper as well. But for now, we're still mostly on the scanning LiDAR. Here I put a picture of, this is actually just based out of the Kitty data, so nothing confidential, but it's an interesting combination of LiDAR and camera here. So these lines are the point cloud from the LiDAR. This is a Velodyne 64. But we also had a camera next to the LiDAR, and we actually projected the pixels on the point cloud. So it gives you an image like this. And we believe that actually this combination of the two is going to be very powerful, because now you have the high resolution of a camera, you get the color of a camera, but you get the depth of a LiDAR. And so now seeing that, for example, this is a car, becomes fairly obvious, because it looks like a car and it has the shape of a car. So that's lots of very useful information. And so I guess to answer the question, LiDAR or no LiDAR, personally I believe that at least in the short term, LiDAR is absolutely needed for a self-driving car. In the long term, the vision may be right. I mean, the vision that you can do it with camera only. The argument is human can do it. But the fact is that today's cameras are not as good as the human eye in terms of dynamic range and even resolution. And also the processing, the human brain is still much better at processing an image than what we can do today, even with more advanced AI. Of course, AI is advancing very fast, but I don't see the intersection in the next 5 years. And then lastly, also, our goal is not to be just as good as human, it's to be better than a human. So if we just start with the same limited sensors as a human, it's a handicap. Yeah, I mean, there is the biomimetism is like always an interesting thing, but the fact is that it's always useful to look at how humans or how nature has solved the problem, and there's always a lot to learn there. But it's not like we have to do it exactly the same way. For example, we don't do cars with legs, and we don't do planes that flap wings, right? So it's just like we have different technology than what nature has access to. And so the solution may not necessarily be the same, yeah. So just a couple of examples also why camera I think could be limited. This is a little bit corner cases. I think the most important one is this one. So if you don't see anything, that's normal. There is a black pedestrian here at night. So maybe people close by can vaguely see a pedestrian. You see the two shoes here. So that's the hard case, right, for a camera. It's very hard for a camera system to see a black pedestrian at night, and that's for sure like a real use case, not something that's imaginary or something. And then of course, you can increase your lighting. You can maybe light in infrared more than what the low beam light. And then as I said, the sensitivity of the sensor is definitely increasing with new generation. The sensors are better and better. But it's always going to be limited, and this case is actually very easy for a LiDAR. And that's unfortunately a little bit similar to the Uber accident that happened last month in Arizona. These are more corner cases, but just to show the concept. This is some painting on the road of a girl. I mean, this has been done so that people pay attention to kids, walking on the street. And then, of course, like you feed this to a neural network for pedestrian, and it will, of course, say, hey, there's a pedestrian in front of you, please stop. Where is it something you can actually drive over? And this with this with a Lidar is easy to filter out. So this is kind of a corner case. This is extreme. But and there's another interesting view here. I think this is in Iceland or somewhere. They've been painting 3D. So it's really painted, right? So something, if you were to look from a different angle, it would look like this. That is just an effect. So I think this is really a corner case. But it's the point is to show that because of the lack of depth in vision, it makes the problem much harder. We know it can be solved, right? I mean, there's like humans actually can solve it. So the information there that it can be solved, but it just makes the problem so much harder. And like because this problem is overall very hard, if there's places that we can make our life easier, I think we should just do it. So this was on Lidar. Another question is HD map or no HD maps, high definition maps. So here, I think, so basically, yeah, an HD map, for people who don't know, it's like today's maps, you roughly have, I mean, you have all the roads, and then you have a couple of points on the road that shows roughly the geometry of the road. Now you start have a number of lanes, so they can give you a lane by lane or turn by turn guidance. But an HD map is where you really have a detailed geometry for each lane. So the geometry is very precise, that it would be within a couple of centimeters exact, and like the curvature would be really precise. And then, of course, like the number of lanes is there, and the connectivity between each lane, like, okay, from this lane you can go here, but from this one you cannot go here. Have much more information, like traffic lights and the exact position of traffic lights, potentially traffic signs as well, and potentially some obstacles like the center divide. Everything would be on the map. And I think that's where there's actually some debates, is like how far do you go in putting things on the map. Like, so the extreme of, for example, the Google approach or the Waymo approach is to put like really dense maps. So pretty much the whole point cloud that you recorded from a previous drive or doing your mapping drive, and then you're trying to match your new point cloud with your measured point cloud. This is also typical robotics approach. It works well, but it makes like really big maps. So in terms of updating this, keeping it up to date, downloading to the car, storage and everything, and even processing at runtime, it's pretty heavy. So our approach is more to say, okay, we need to put the information that we need for driving, so obviously the lanes, and but then for localization, let's just focus on some landmarks. So typically, poles are good landmarks. So traffic light poles, street light poles, traffic sign poles, because they're fairly easy to identify. And then they make a good, what's it called, lighthouse or things that you can use for triangulation. But also, the lane marking are very good landmarks, because especially the lane lines, because that's at the end what you need to follow. So even if your map is a little bit off, but you adjust your map to the lane line that you see, then you're actually going to drive in the center of the line. So that's an important, very important lane mark. And so then there's people asking, like, well, do you need HD map at all? Like, as a human, you can drive without an HD map. You know, okay, I need to go that direction, and then just locally you figure out, okay, I'm going to drive in this lane, or I'm just following the lane, and everything's going to work fine. The way I look at it here is actually, as a human, you still have a little bit of a HD map in your head, in the sense that if you've driven there before, you drive much more confidently that this is the first time that you drive in a place, because the map is kind of actually like the long-range sensor. It's something that tells you what's coming after what you can see directly, like how are this lane going to merge in the future? Is this one a right turn lane or a left turn lane, or which lane can I use? Is there a curve coming, in the future, and so I should start slowing down? And So the way to look at it is basically you have your camera, Lidar, which are your short-range sensor, 0 to 100, maybe 150 meters at most in urban environment. And then you have the map, which is your long-range sensor. And then you fuse everything. And in the short range, you put more weight on the actual sensor. And in the long range, you put more weight on the map. So that's, I think, what I wanted to say on maps. Then artificial intelligence or no AI. That's actually also an interesting question, and I think also that's where these two worlds that I mentioned before, the automotive world and the high-tech or software industry, have different views. And it all comes down to safety and validation and how you prove your thing is safe. That's the main worry currently in the automotive industry, where we've been used to being able to prove that the thing is safe, and that I totally understand the behavior of what I'm designing, and then I can say kind of by design my thing is safe. And I think we reached the limit of such an approach, and also we have access now to technology, and the main one being data, actually, that offers other alternatives to proving that something is safe. Of course, at the end, you still need to prove that it's safe. That doesn't go away. So the way is, of course, like with AI, now you have a black box. You train it, and then you say, I've trained it, and I've done some statistical tests, and it seems to work. So let's hope for the best. So that's, of course, worries people like safety engineers and regulators. But I think the fact is that, it's not just like a statistical test on a couple of hours of driving. Even though, just a side note, I mean, it's interesting that when you test the human drivers, the test is like 20 minutes. And you see someone driving for 20 minutes, and you say, yeah, this guy knows how to drive. I'm going to give him a license. But for machine, the bar is a little bit higher. But so I think I mentioned data, and I mentioned hundreds of petabytes. Today, it's actually possible. It's going to be, somehow expensive, but it's within reach that you have if you have 1,000 cars driving for 3 months, you're going to collect 20 million kilometers of data, and that's a lot of data. I have another slide on what's good enough. But that's already, you can prove that you're better than a human with such a driving. So this one is not solved, and there's trying to be some way saying like, okay, we use AI for comfort driving, but the safety path is independent of AI. This would be nice if it worked, but personally, I'm not sure we can actually go around trying to find a simple path that we can guarantee is safe. I think, unfortunately, it's not possible. And then just to illustrate here, if people don't know, so this is like semantic segmentation. So it's a neural net putting a color or like a class on every pixel to say, okay, this is a car, this is free space on the road, this is non-free space, this is trees, this is traffic light, this is pedestrian. So you train a neural net to classify each pixel in an image, and then from there you can then group them and extract objects and build your environment, as I mentioned before. So one of the area where AI is going to play is prediction. So for example, here there's this pedestrian crossing, you lose him, and then he crosses without looking. Of course, here there's a red light, right? So it's the right thing to do. But you could imagine that the same thing happens with a green light. And then how do you react to this, where the pedestrian just shows up at the last minute? And then also, even when you see the pedestrian, like when it comes right here, you could question like, okay, is it going to stop or is it not going to stop? And if you pay attention in urban driving, it's actually very, very hard, because people would stop, sometimes like maybe 50 centimeters or less than a meter from a car driving at 50 kilometers per hour. And the way we drive as human is we say, well, this guy is actually going to stop, so I'm going to continue. it's real, and there's actually lots of clues. If you start looking, it's typically if you make eye contact, like if he's looked at me, you say, okay, this guy saw me, so he's going to stop. I have the right of way. He saw that there's a car coming, so he's just going to stop. But that's already hard for a computer, meaning you need to do, at this distance, like face recognition and like eye tracking, and did he look at me or not? Maybe, is it someone looking at his cell phone? This kind of clues we will need to identify. And then even things, so this is an example that's fairly common, right? This is just me recording this. It happened to me, so it's not something on the internet or some unusual case. I'm sure everyone has seen that. But now just think of a row of parked car, like we had on the picture before, and someone coming in between two cars, and so you could actually, for example, do some calculation and say, hey, I will always leave a distance to the side or lower my speed so that every time there's someone coming between two cars, I will actually have time to sit and have time to brake. So that would be very nice. But then you do the math and you take a street in Munich, and if you drive on the rightmost lane next to parked cars, you would drive at 20 kilometers per hour. So no one's actually doing this. So everyone kind of assumed that this is not going to happen. And so that's a hard question, right? I mean, do we release a product that, okay, is safe because like from any occlusion, if a pedestrian comes by, I can stop. But then, I'm drive 20 kilometers per hour. How many customers am I going to have? Not super clear. Or do I take, okay, like a pedestrian can come by, but it's unlikely, so I'm just going to take the risk because the risk is low enough in the grand scheme of things that I'm going to drive. And the day it happens, I'm just going to come back to the regulator like, yeah, this was a non-risk, and every human is taking the same risk, and overall I can justify. I've now driven 100 million kilometers, and this is the first time it happened, so it's still reasonable. But so that's where I think that's where prediction actually plays a big role because it's not going to solve the problem, but it's all about lowering the exposure. So detect some clues. So in this example, maybe you've seen the pedestrian before, you lost it, but you're able to keep tracking and predict that there's someone coming. So it's all about lowering your exposure to such risky situation. And so conclusion on prediction, I think prediction is absolutely necessary. And actually, whether you use AI or not, I think you're going to use AI for it because it's hard to define with rules. But what's sure is that it's not going to be 100%, and I think it's already good if it's 99%, but it's not going to be 99.999%. And but still, 99%, if it lowers your exposure by 99%, is still 2 orders of magnitude that you get in your overall safety. So it's still good, and so because this is going to be AI based and not well defined, but is important. That's why I think the overall solution cannot be without AI. And then once you start using it in one place, then why not use it in another place if it improves the overall performance, because you already have the issue that you need another proof for validation than just pure design and rules. That was on prediction. So then my last slide is like what's an acceptable goal, right? How safe should we be? And here I'd love to hear your feedback after the speech. Basically, if you look at humans today, especially in urban environment, it's actually really bad. There's an accident, like a touch accident, roughly every 100 to 200,000 kilometers in the city environment. Deadly crash, of course, are not as high, but they're still pretty high, right? I mean, like the car industry actually kills way more people, at least in Europe, than the gun industry, for example. But 95% of this is because of the drivers. Very few due to mechanical failures or other failures from the car. And so it's all about, like actually Waymo coined the term, but it's all about making a better driver much more than making a better car. And so what we think is that actually when it's better than human, we should release it. So of course we want to have a little bit of margin, like strictly when it's 1% better than a human, that's a little bit too soon because there's going to be some uncertainty on how we measure that. But we kind of shooting for like when it's 10 times better than a human, we should release it because otherwise it means we keep killing killing people on the street while we have a technology that could save 90% of the people, but we wait just because it's good enough. Of course, the other way to look at it is this would be killed by machine, not by humans. And if you look at other domains like aerospace or even in the industrial or I guess even automotive today, like what are the safety goals for level 2 systems or level 1 system? You're typically talking about what they call ASLD, which is typically 10 to the minus 8. So like one very bad issue every 100 million hours. So that's, if you take a speed of 20 kilometers per hour average speed, that's every 5 million, every 2 billion kilometers. And so if we today, humans at 200,000 kilometers between incident, that's let me get this right. This is you do it as like a 5 order of magnitude, 5 order of magnitudes higher. So if we're shooting for 10 times better than a human, we would still be 4 order of magnitudes below what's typically done today for a machine. So it is a big question. But I think, again, like the right way to approach it is to say, okay, now first let's replace the human, and then, okay, my time is over. And then, of course, we're not going to stop there. It's like emission, for example. Like each year there's new targets for emission, and it's going to be the same for autonomous driving. We'll start 10 times better than a human in maybe 2020, early 2020s. Maybe in 2030 we want to be 100 times better than a human, and 2040 we want to be 1,000 times better than a human. So I think that ends my talk. So now we have a little bit of time for answering. We are hiring also in Munich, so if you are looking for a job, feel free to reach out. We're looking for passionate, motivated, competent engineers who can help us solve this very challenging problem.
So, thanks for the fascinating talk. We have 10 minutes for questions. I'm sure we have some.
Thank you. A short time ago, I read an argument against the highest levels of automatic driving, and it was something like that. Imagine there is an obstacle on the road, and there's a policeman standing and telling you
yes.
to enter some way that you shouldn't under normal circumstances.
Yeah.
Do you think that's going to be solve that problem of things that you don't really expect?
Yeah, so I think the policeman, that's actually very expected, right? I mean, this is fairly common. So the approach to this is, I think, 2 levels. First, we're going to have at the beginning like a remote control for the car, not just to take over or to watch it all the time, but the car is going to be able to detect that, okay, here there's something weird, something I cannot handle. It's going to stop, go into a safe state, and then call the remote center, and someone is going to dial in, look what's going on, say, oh, I see what's going on. Yeah, this is the path you need to do. So that's probably going to be the first step. But then also, I think actually it's going to be feasible to recognize policemen. At the beginning it's just a pedestrian in the middle of a road, and then it has some sign that it's a policeman. So I think it's not going to be that difficult to recognize that it's a policeman. And then the gesture recognition, there's actually also a lot of gesture-driven. Now it's more like what's called like games and infotainment system. But gesture recognition is also not necessarily that hard, especially if you have Lidar and you have the 3D view of the pedestrian, of the policeman. And then also, I think that's where there's a difference between safety and comfort or doing the right thing. That the car will still never, of course, drive over the pedestrian or go into someone else's path, it's still going to make sure that that it's a collision-free path. So worst case, it's going to look stupid, but I don't think it's going to do something unsafe in that situation. Yeah.
So
hi. My question would be, or two short questions. What is your opinion on the approach of Tesla currently of doing like massive neural network learning, like with a fleet of all the produced cars on the street having the sensors and learning? So this is like contrary to the algorithmic approach. And maybe one short second question. We saw all the sensors you mentioned, and one sensor I'm missing there is microphones. Because if I'm driving not in Germany, but for example in India, you have to hear if there are cars around you. And
yes.
It seems to me that this sense, like hearing, is ignored.
Yeah, so actually, I did mention it. We plan to have a microphone in the car. At this point, mostly for emergency vehicles, policemen and firefighters. For detecting other vehicles, I still think we have the other sensors that will still detect, right? I mean, that's the difference with human. Humans use their ears to get 360. We use, all the sensors 360. So there's Lidar looking in the back, there's cameras looking in the back, radar looking in the back. So detecting vehicles, I'm not too worried detecting them with this. But it could be for the ones that are, far away, like an ambulance coming. That's where we need a microphone, or also maybe to detect that this is an ambulance and that we need to yield to this vehicle. Yeah. And the other question, about Tesla. That's a more loaded question. I guess it's another debate, like whether it should be a full AI path, like pixel to torque, they call it. This is actually not what Tesla is doing at this point. It's using AI for perception, and there's still a more traditional path planner. Then I think the approach of using data from the fleet, I think that actually makes a lot of sense. And I'm actually trying to push the mothership to do the same thing, and it's slowly coming. Because like here, my experience developing the level 2 system, this is just so powerful. I mean, it's arrogant to pretend that you can think of all the corner cases up front. So of course you want to do enough testing that you don't miss the obvious things. But then like the kind of things you can see when you have a fleet that does like 3 million kilometers or miles per day, it's just like very impressive. Like things you think could never happen or you'd never think of, and you see, and then you can you just have all the data and you can do something about it. So I think that's actually I think in Tesla's biggest edge is this ability to do things in the fleet. As I mentioned before, I don't believe in the sensor suite. I mean, I think it could be okay maybe for level 3, for sure for a good level 2. But I'm convinced not for level 4, especially in urban environment. So I think that's the limitation, and that's where, I think it's like I'm not sure how they're going to hold the promise of saying they can do full self-driving with this hardware. But it's going to make some good products. So if people are happy with what they get, maybe that's how it's going to solve it.
Let's take a question from the back.
It seems like there should be a common test center of all the car manufacturers in which you can share the different test cases that you have either created by simulation or that you have recorded in traffic. And that would require some level of standardization. Can you tell anything about that?
Yeah, absolutely. This is where we're going. That's where the whole industry is going. There is some convergence on what format to use for the scenario for simulation. There is a VDA-driven project called Pegasus that takes all the German automotive industry, but also open to like other European manufacturer. That's actually focusing on just this, like defining the test cases, so like kind of a Euro NCAP approach of what are the test scenarios to do, both for proving ground testing and simulation. And of course, you need to do some testing on proving ground. But I think at the end it's going to be like 10% of the validation, and maybe 50% is going to be a simulation, and the remaining 40% is going to be real world driving with a safety driver.
Hi. Do you have sensors that can look through objects?
So the radar actually has this interesting property that the waves can reflect around obstacles and under obstacles on the ground. So one actually use case today is the radar can track the car that's in front of the car in front of you. And so we actually implemented that at Tesla, and it made a big difference. There was someone capturing this on a dash cam, showing that the system started alerting the driver and braking before the car in front of you of this driver was braking. And this works actually pretty well because if you think about it, when you follow a car, you could potentially leave only the distance that corresponds to your reaction time. So for an autonomous system, it's like 100, maybe 200 milliseconds. So this would be very close, right? At 30 meters per second, that's 6 meters, just the car length. Of course, you want like leave a little bit more because people are not comfortable. But essentially, if you were to leave something that close, then you can always brake as much as the car in front of you. And so the only case where you don't avoid the accident is if the car in front of you brakes more, which the only way they can do it is if they get the help of another vehicle. Basically, if they bump into another vehicle. So now if you're checking the car in front, you're down to, okay, now you can have an accident only if it's a 4-car pileup, which reduces the occurrence quite a bit. And actually just makes me think of another anecdote of the distance, the gap you want to leave to the vehicle in front. That's why it was interesting to get data also from Tesla, that we would see that the number of accidents, there would be a sweet spot of around 1 second time gap. If you get a little bit closer, then it increases a bit again because you don't have enough reaction time. But also if you leave a longer time gap, the accident rate increases because now you often have even enough space for people to do a cut-in, which is dangerous as well. And so there's actually a sweet spot where you don't leave enough space for people to cut in, but you still have a distance. And so that's kind of interesting because at school they teach you to leave 3 seconds. And we actually had data showing that, well, 3 seconds is actually unsafe given how people are driving. So that's also going to be interesting questions of how we adjust the driving code for self-driving cars, which have different reaction time and different capabilities.
So I think we have time for one last question.
So concerning takeovers, you said that there are 10 to 30 seconds that the driver needs to take over. So how much can current sensors in this level 3 car that you showed can give the driver to take over?
Sorry, how much second?
Yeah, how much seconds of leeway can the sensors in the current cars give the driver to perform this takeover? So like 10 seconds or more?
The exact number, you mean between 10 and 30 seconds? So there's no real standard in the industry yet. On the A8, I don't know it by heart. I have to check what's the value. But it's like here, this is roughly the range, and then each manufacturer is still making its own analysis to say if it's if 10 is okay or if you need 30. But I guess typically the idea is that the driver is not expected to handle an emergency situation. So you cannot expect the driver to be doing something completely else and then understand what's going on and do the right thing. This we know doesn't work. So it's just about you need to do your own measurement of, okay, someone is doing something completely different, and now they come back. How much time do they need to understand the situation and switch back to driving mode and so on. And so people are doing some studies to figure this out, but it's in that range.
So unfortunately, we are out of time. Are you still around?
Yes. Yeah.
So come directly to Alex for remaining questions. And thank you again.
Thank you very much.